Hello everyone, our paper is titled, Walking in the Wild, Safe and Natural Redirected Walking in Open Physical Spaces. We focus on improving walking experiences in virtual reality. In traditional VR settings, users usually move within small, fixed spaces, where the boundaries and obstacles are well known. In these environments, user trajectories are also predictable, which makes it easier to redirect them smoothly while keeping them safe. While classic redirected walking works well in small, controlled environments, it becomes difficult to use in large, open, and dynamic spaces. In real-world public settings, there are no fixed boundaries, obstacles can appear or move unexpectedly, and multiple users may interact at the same time. To address this, we introduce a new task, called Open Physics Spaces Redirect Walking, and propose a method named Dynamic Control and Redirection. It uses real-time optimization and safety constraints to guide users naturally while avoiding collisions. In our method, Dynamic Control and Redirection with Safety Constraints, there are two key components that make everything work: dynamic control barrier functions and quadratic programming. First, let's talk about dynamic control barrier functions. In the open physical spaces redirected walking setup, users interact with dynamic obstacles. These can be other users, physical objects, or unexpected changes in the environment. So, dynamic control and redirection needs to ensure that users stay safe from collisions no matter what. Essentially, we calculate the distance between the user and the obstacles and turn that into a safety function. The safety function ensures that when the user gets too close to an obstacle, the system will automatically adjust their path to keep them safe. Now, let's move on to quadratic programming. In practice, when a user gets too close to an obstacle, or when the path is blocked, the system might face a dilemma. Traditional optimization might fail to find a solution. That's why we introduce a relaxation mechanism. This means, in some extreme cases, the system allows the path to be a little more flexible. It might let the user deviate slightly from their intended path, but it also applies a penalty for any safety violations, making sure that even in the most complex situations, the solution is still feasible. While safety is our top priority, we also want the user's movement to feel natural and smooth. If the user's path deviates too far from what they intended in the virtual world, it can break the immersion and even cause motion sickness. This is where quadratic programming optimization comes into play. Quadratic programming helps us find the best possible velocity for the user, one that avoids obstacles while keeping the user's path as close as possible to their intended direction. Our approach jointly optimizes the user's desired velocity in real time, by coupling dynamic control barrier function safety constraints with a relaxed quadratic programming objective, ensuring collision avoidance in open, dynamic physical spaces while preserving natural, immersive VR locomotion. We compared dynamic control and redirection with 7 state-of-the-art redirected walking methods, including S2C, S2O, a PF variants, and learning-based approaches. To test their performance, we created a simulated environment with random walking paths and dynamic obstacles. We used 3 key metrics: reset count, how often the system had to interrupt the user; virtual distance between resets, how far the user could walk without interruption; time elapsed between resets, how long the system ran smoothly before a reset. It improves performance by around 30% to 50% over most baselines. We also conducted a user study with 30 participants walking in a real VR setup, using for different methods. In all 3 metrics, dynamic control and redirection outperformed the others. Users experienced fewer resets, walked longer distances, and spent more time navigating without interruptions. To assess user comfort, we used the simulator sickness questionnaire. Thanks for watching.